Welcome. In this video, we are going over the big idea of universal gravitational force. It's the force of gravity, but now we're looking at it in how it interacts with things like planets and moons and satellites and stars, just at a larger scale. Now, this video, we're actually talking about 4 different things related to this universal gravitational force, so let's go ahead and dive right in. The first thing, part A of my notes, universal gravitational force. There are really just a handful of fundamental forces in our universe. One of them is the electron, or the electric force that attracts and repels charges. Another one is an attractive force between mass, things with inertia. Okay? And this force is always attractive. And this fundamental force has this equation. Here it is. Okay? This universal force of gravity, whether it's between an apple and the earth or between you and your computer. Technically, you and your computer have some mass. There's an attractive force between your two objects. Now, that force is really tiny, as we'll see in just a second. But any two masses, all right, there's always an attractive force. The equation is based on G. G is just a constant. It's called the universal gravitational constant. Follows from the name here. And it's 6.67 times 10 to the negative 11th. This is a very small number, which means if you have small masses, this is going to be a very small value. That's why you're not feeling attracted to your laptop computer. You're not feeling attracted to other people when you're walking past them in the hallway, even though technically there is an attractive force on them. The units here are Newton meter squared over kilogram squared. This is on the AP physics equation sheet. You don't have to memorize it. Okay, and these are the two masses. Similar to the electric force, it's always between two masses. You can't have a force of gravity with one object all by itself. Okay, it's always two things that are attracted to each other. So this is the mass you put in kilograms. R is the radial distance. It's how far away they are. A lot of things in the universe are orbiting one another. So we don't really talk about measuring things in like the x direction or the y direction. It's the radial direction. That's going to be between the centers of those two objects. So I have this diagram. If I wanted to find the gravitational force acting on each one due to the other, it's G m1 over m2 over r, the distance between their centers, squared. Okay, now if we were looking at things like on the Earth, well, r is still going to be from the center of the Earth all the way essentially to the surface of the Earth. Okay, this is just going to be the radius of the Earth. Technically, we should be doing it like to the center of the person, like to your belly button, but that's such a tiny distance compared to the radius of the Earth that it doesn't matter. So if you ever use this equation to find the force between like the Earth and like a tree or something, you're just going to plug in the radius of the Earth right there. Now, here are a couple of values that can come in handy. You're not expected to have these memorized, though, but we can see them on homework problems. Okay, on the AP exam, they'll be given to you. The mass of the Earth is almost 6 times 10 to the 24 kilograms. Obviously, a very large number. The radius of the Earth is a little under 6.5 million meters, 6.4 times 10 to the 6. This is what you're going to see on the AP equation sheet. Okay, it looks very similar right here. They do have the absolute value sign. That's just kind of, again, we're not going to worry about a negative force here, especially when we're talking about these large objects. R won't be negative because, again, it's just this radial distance. Okay, we're not going to say that the R value is negative just because this is to the left. That doesn't really make a whole lot of sense, and it's not really valuable to us. Okay, next slide. Well, part B is called acceleration due to gravity. All right, and this is directly coming from our last slide, this gravitational force. All right, you're probably used to this equation. This is what we used before, W equals mg. And we're really talking about the same force here. These are the same forces. But when we've used this equation, we've kind of been cheating, or at least we've been simplifying things. This equation is only valid for the Earth. Okay, and if you've ever wondered where this G equals 9.8 thing is coming from, it's right here. Here's the force of gravity equation. Let's apply it for just a person on the planet, just one of us. Or it could be for an apple on the Earth, or a bird, or an animal, whatever. Okay, if we were to apply, I guess a bird's an animal. If we were to apply this, we would plug in 6.67 times 10 to the negative 11th. One of these masses is the mass of the Earth, m1. One of them's the mass of the other object, and r, remember, we're going to use the distance from the center to the surface. Well, right here, 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24 divided by 6.38 times 10 to the 6 squared gets you 9.8 meters per second squared. That's where that value is coming from. This equation is really this equation, but we've just been simplifying this whole thing. Because if you're staying on Earth and you're essentially staying on the surface of the Earth, well, this is always going to be the same value. This is also why technically g decreases when you gain altitude. Not by a whole lot, but it does a little bit. So this is 9.8 meters per second squared. That's how those units break down, and that's how we've been using this equation. Okay, but they are officially the same equation. Now, the next slide, still in that part B, the acceleration due to gravity, what we've been describing as g, can actually be used for any planet. We've always been using it for the Earth, and maybe you've heard in problems they say like, oh, like the moon has a force that's 1/6 as much. We can still talk about g for other objects like the moon, the planet Mars, okay, and so on and so forth. So this acceleration due to gravity is used much more broadly than just here on planet Earth. But it's always this form. It's g multiplied by the mass of the object, the mass of the moon, the mass of Mars, divided by the radius of that object. It's the acceleration due to gravity for that object, this lowercase g. And so on the old AP Physics exam, they gave you the equation in this form, which is exactly this right here. However, on the AP Physics 1 equation sheet, they're doing something a little different. They're representing g, even though it's meaning the same thing, as the force of gravity, this thing, divided by m. But it matches, right? G is this blue box here. If I kind of solve for this blue box, I would take Fg and I would divide by m2. That's it right here. But it's representing the exact same thing. Okay, it's still something in meters per second squared, though actually the AP equation sheet, if you look at this equation, G can also have units of newtons over meters, and I've seen that shown up on the AP exam. So don't be confused. The acceleration due to gravity, yeah, we've most commonly seen it represented as meters over second squared, but you could also say, oh, on Earth, it's 9.8 newtons over meters. Okay, also, oh my gosh, just to make things a little trickier, G is also referred to as the gravitational field strength, which is going to guide us into our next video. It's often actually convenient to look at G for an object versus the force. If I said like, oh, on Mars, there's a force of gravity of on an object of, I don't know, think of a number, 150 newtons. That's actually not a very helpful number, because if I don't know the mass of that object, remember F equals ma. Okay, if I don't know how massive that is, this doesn't tell me if that object will be accelerating a lot or accelerating a little. The advantage of using this, g, is it's telling me how much force is on every unit of mass. So on Earth, it's 9.8. Every object on Earth has this 9.8 meters per second squared downward. On Mars, or I'm sorry, on the moon, it's about 1/6 as much. So you know for every mass, it has an acceleration of 1/6 this value. It's a little more meaningful if you're thinking of it from an astronomy point of view, trying to understand how objects are interacting with those large, massive bodies. Okay, but Part C, gravitational fields, this will go pretty quick because it's pretty straightforward in how we're going to look at it. We have to know what a field is, and a field really is just showing the direction and the strength, and I'll talk about this a little more later, of force X. For example, this diagram right here, this is showing the field the force of gravity is acting on. And just think about it. Everywhere around us, gravity applies a downward force. We've been doing that forever. The same thing is true. If I have a little apple, if I dropped it right here, it's going to go straight down. If I dropped it right here, it would go straight down. If I dropped it right here, it would go straight down. If I dropped it here, it would go straight down. These lines are representing the force and also kind of the path that those objects are going to accelerate, that they're going to feel a force from. And so on Earth, especially in this kind of zoomed in kind of scenario, it's really easy. The strength of the field, they also use G. So you might see the term or the phrase, the strength of gravitational field, or of a gravitational field, ... On Earth, the strength of the gravitational field is 9.8 meters per second squared. It's weird. We haven't really referred to this number as that. Remember, or it could be 9.8 newtons over over kilograms. Okay, oops, I'm sorry, that's what I should write, newtons over kilograms. Oh my goodness. Right here, newtons over kilograms. Let's make sure we're nice and clear. Excuse me. But it's just representing how strong this field is. Okay, and it's pretty easy to draw. If we zoomed out on the Earth, well, it's maybe slightly more complicated because, of course, the Earth is a sphere. So those arrows would no longer look perfectly straight down. All right, they would look more spherical. But the same thing applies. If I just took a little mass and I just released it right here, gravity would pull it inward. If I took a little mass right here, it would pull it inward. Now, you could draw gravitational fields for multiple objects, and again, it gets a little trickier, but the path still represents the same thing. It's the direction the force is acting. If I'm close to the moon and I drop a little mass right here, yeah, there is a tug from the Earth, but because I'm so much closer, kind of the moon wins the tug of war, and the object goes in like this. If I had an object right here, the Earth would win. It would get pulled like this. This is pretty interesting. If I took an object and placed it right here, well, yeah, the moon's pulling on it, but the Earth is tugging on it too. If it's a little closer to the moon, it might follow this trajectory. What do you think's happening right here? This is where the net force from these two different objects would be canceling out if I had some test mass. If I took a little rock and I placed it right here, both of these two things are tugging on it, but the net forces would be equal from those two things. Therefore, they wouldn't be accelerating. Okay? There are official rules for this, though we're not going to spend a whole lot of time drawing these. Okay? But the lines are always attracting towards mass, because remember, it's an attractive force. By rule, we don't have the lines cross. This would be confusing if we had these lines crossing each other. We always have them maybe get closer, but we never have them cross. They are always going to hit the surface at 90 degrees. At 90 degrees. It just helps keep our diagrams nice and clear. Okay? And if you have lines closer together, it's representing a stronger force. Okay? Here, when you're farther away from the Earth, because that equation is based on R, well, there's not as much force. If you're really close, oh, there's more force, and we represent that with lines that are closer together. Okay? So these might pop up from time to time, but we haven't spent a whole lot of, time on them a whole lot. And again, you might refer to the strength as, really, it's just that value of G. Last thing we're going to look at, this is how we're ending our video. We're going to look at circular orbit because we are right in the middle of our circular motion unit. And I want us to look at an example. Let's say here we have the Earth, but it could be anything. Okay, it could be another planet, it could be the moon, and here's something just orbiting that object. You could have something orbiting the moon, or of course the moon orbits the Earth, or the Earth orbits the sun. All right, but we have something that's orbiting around and around. I have a little PhET simulator that I'll show you, pretty basic. Okay. Here is like the Earth. Here's the sun. This is representing the forces. How should those forces compare? Hopefully you recognize they should be even by Newton's third law. Okay, and of course the Earth is moving around and around. If I look at the path it's tracing, we're not going to sit here all day, but it's tracing out a circular path. And look at this. This red arrow is representing the velocity. Notice it's a tangential velocity. Things in orbit obey circular motion. Now, even if a lot of things in orbit are actually doing it in ellipses, so more elongated paths, just like we talked about before, we can still approach it as circular motion. So that's the last little thing we're going to look at, how we can apply circular motion to objects that are in orbit. So I'm going to go back to my PowerPoint. Well, we're going to look at this mass here. And if I was to draw a free body diagram for it, there's just one force, F, and this is the gravitational force, okay? This is Fg right here. Well, let's set up the sum of the forces acting on that object, and it's towards the center of this circle it's going in, so it's toward the centripetal direction. Well, it's just Fg. Well, the sum of the forces in the centripetal, that's the mass of that object, the mass of this moon, or from that simulator, this would be like the Earth, but the mass of that object times its speed, v squared divided by r. And what's Fg? G, little m, big M, because that's this thing right here, divided by r squared over m v squared over r. Couple things to notice. First, the mass of the orbiting object, this thing right here, actually cancels out from the equation. If I kept going and I solved for v, the speed of that object does not actually depend on how massive this thing is. It depends on how massive the Earth is in this example. It depends on how far away you are, but it doesn't depend on how massive this object is right here. Okay, that's the first thing to notice. If I kept solving, okay, I'm going to multiply one of these r's over, and that's going to cancel one of these r's, but not both of them. I'm going to have g, the mass of the Earth, divided by r and the square root. This is the velocity of things orbiting. How quickly things are orbiting around an object in our universe are based on these three things. Now remember, this is a constant. The other thing to notice on this slide right here, I've reset, I have my equation right here. Of course, we said the masses cancel out. Okay, I also know that v is equal to 2 pi r over t, if we're assuming these things are traveling in circular orbits. If I rewrite this, I have g me over r squared equals, well, I'm going to have 4 pi squared r squared over t squared divided by r. That's me plugging in for v right here. If I simplify, that means I have g me over r squared equals, here I have just 4 pi squared, one of these r's cancel, r, over t squared. Now, I'm going to swing my t squared over here and my r squared over here. That's going to get me t squared times g me equals 4 pi squared. Careful, when I swing this r squared over, there's an r already here. That's r cubed. And this is very interesting because this right here, g times me, for the Earth, this is just a constant. And 4 pi squared is just a constant. Well, for any object like the Earth, the period, the time it takes an object to go around once, well, it is directly related, or there is a relationship, simply between the radius of how far away it's orbiting. Or I shouldn't say these are equal to, I should say they are proportional to, they are related to. This is actually known as Kepler's third law. Johannes Kepler figured this out from experimental data back in the late 1500s. And Isaac Newton's laws actually prove that this is true. Since these things are constant for the Earth, you could actually figure out, you could approximate how long it takes an object to travel around and around just based on how far away it is. So that's an interesting fact. You don't really officially have to know Kepler's laws for this class, but Isaac Newton was able to prove a law 100 and so years after Johannes Kepler did it just by looking at things like planets orbiting the Earth, or I'm sorry, planets orbiting the sun. Okay? Oh man, that was a lot of information. Thanks for sticking with it. That's the end of my video.